Effective energy management is crucial in minimizing environmental impact and optimizing operational efficiency in buildings. This report will be focused on the Energy Management Environment Audit project conducted on Village 1B, which is a student dormitory in University Technology Petronas, Bandar Seri Iskandar. The project involves a comprehensive analysis of the building's energy performance through a building envelope audit, energy audit, and orientation audit. The orientation audit assesses the building's alignment relative to the sun and wind. Understanding the building's orientation can inform strategies to maximize natural light and ventilation, reducing the reliance on artificial lighting and mechanical cooling and heating. The building envelope audit examines the physical barriers such as walls, roof, windows, and doors, which separate the interior of the building from the external environment. This audit evaluates and determines the areas where energy loss may occur, thus allowing an evaluation to further improve any insulation and sealing that is necessary to enhance energy efficiency. The energy audit evaluates the trends and behavior patterns of the building, which allows the identifying major energy consuming systems and appliances. This audit will expose any efficiencies that are present and to provide recommendations for appropriate measures to reduce energy and costs. The problem arises where Village 1B currently is undergoing a number of significant challenges relating to energy efficiency, thus resulting in high operational costs and an increased environmental footprint. The building's envelope has several areas that contribute to energy leakage. The energy consumption of the building is also not optimized, while the orientation of the building does not take full advantage of natural light and ventilation. These issues contribute to excessive energy use, higher utility bills, and may have a direct repercussive impact on the environment. Thus, this project aims to address these challenges by conducting a comprehensive orientation, envelope, and energy audit to expose any efficiency and propose solutions to improve the energy performance and operational sustainability in Village 1B.
It is important to understand the layout of a building for conducting an environmental audit, especially the orientation aspect, as it has a permanent effect throughout the service of any premise or facility. This is the plan view of the V1 ground floor with its exterior dimensions of a length of 90 meters and around 20 meters. So the ground floor consists of 24 twin sharing rooms on both sides, four single rooms right here. Um, it also has the main entrance right at the center with two right beside the single rooms, and there's emergency exits and bathrooms um, on each side of the building. A crucial aspect of building orientation audit is to study the sun paths over it and understand its effects, as it has a major role, especially in hot and humid tropical countries like Malaysia. The figure shows the sun path aligned to V1, which is specifically simulated for the V1's geographical location and sun zenith angle. So sunrise occurs in the northeast direction, which is the back of V1, with the sunset at the front of the building in the southwest direction. So the peak sun exposure is right on top of the building, which occurs approximately around 1:15 p.m. So the timings and the durations of sun exposure directly contributes to the demands of ventilation, cooling, and lighting energy consumption. The figures shown here illustrate the effect of the sun movement across the building at different times of the day. The sun exposure provides natural lighting, reducing the need for artificial lighting. However, the heat gain from radiation increases the demand for ventilation and cooling. So as you can see in the diagram, before noon, around 7:30 a.m. and 10 a.m., the lighting demand is low for the back side of the building with high ventilation and cooling energy demands because of the heat. And towards the noon and afternoon, it is vice versa, where during the evenings, the front requires more ventilation and cooling energy supply, and lesser lighting is needed because you have the evening sunlight. This figure illustrates the air movement which obeys the law of thermodynamics by transferring heat through convection. The hot air is less dense and moves upwards, while the cooler and denser air fills the vacuum created by the hot air moving up by flowing into the building open entrances. Heat gain can also occur by radiation through windows. Hence, to control this, multiple mechanisms can be implemented on the windows, such as as roller shades, reflective polyester films, and also ventilation lines.
Now, in terms of building envelope audit, we should know the characteristics of the building as well as the characteristics of doors and windows. And we should know also the information of the insulation if there is any insulation installed. So, the data of the ground floor of Village 1B have been collected as it is critical in terms of its function as a support for the occupants. It acts as horizontal support and distributes the load across the building supporting structure. So by saying that, the floor data have been collected and recorded as follow. The front door dimension is equal to 210 centimeter height and 328 centimeter width. The ground floor has 28 rooms with 2 bathrooms, one in the left and one on the right. The condition of the floor is considered as excellent and clean. The material of the wall is concrete, and the room area has been calculated as 435 centimeter height and 380 centimeter width. Now, moving forward to the doors, which are mainly to control the access to different parts of the building. They also provide privacy and security by acting as barriers against intruders. Also, doors help to maintain the room's temperature and air conditioning, which will result to reduce the heat loss and noise as well. So the door data have been collected and recorded as follow. The doors area is basically calculated as 210 centimeter height and 90 centimeter width. There are 28 doors in which made of the wood, and the doors condition is considered as excellent. Now lastly, the window, in which are mainly used to control the ventilation inside the room. Additionally, they can be used as heating elements if the room become cold by allowing the sunlight enter the rooms and warm up the space. So the window data has been collected as follow. The window area is calculated as 119 centimeter height and 163 centimeter width. The window condition is basically good, and they are made of glass. The frame material is considered as aluminium. Now, to calculate the infiltration through windows, we convert the windows area from centimeter to feet, in which will result to 20.87 feet square. Now, by considering the window as metal sash window, the coefficient used as follow. with no weather stripping is roughly equal to 1.01, and with weather stripping is equal to 0.44. Now the infiltration with no weather stripping is roughly equal to 295.1018 cubic feet per meter, and the filtration with the weather stripping is roughly equal to 128.5592 cubic feet per meter. So the saving of implementing the weather stripping is roughly equal to 166.5426 cubic feet per meter. Now, in terms of improvements, there are many enhancements that could be done to Village 1B, especially in doors and windows, such as installing weather strip doors and installing weather strip windows, and by making sure that the fans installed inside the rooms are high quality, and which will lead to a better air circulation. Now, the advantages of employing these changes will result in improving energy efficiency as well as indoor comfort, and low maintenance will be required, and which will lead to comfort the students, especially during the semester. Now, the outcomes of employing these changes is going to increase the energy efficiency, as well as the cost saving will be significant from 2 to 3 years. And lastly, it will promote a high comfort.
A building energy audit involves analyzing the performance of various energy systems, including heating, ventilation, air conditioning, lighting, and appliances. So by identifying areas of energy waste and recommending improvements, an energy audit aims to enhance energy efficiency, reduce operational costs, and lower environmental impact. This process is crucial for optimizing energy use, improving indoor comfort, and achieving sustainability goals. So the building energy audit took into account regarding the building's environmental temperature, relative humidity, and the light intensity. The process into acquiring these data was by measuring the temperature of the internal and external environment using an infrared thermometer, while the relative humidity was measured using the humidity sensor, and the light intensity was taken using the light meter. When we conducted the light energy audit, we found that the light of fixtures are fluorescent light. So there were a number of light fixtures per room and 21 light fixtures in the corridor. There are 28 number of rooms and the total number of light fixtures on the floor is 77. The rated power for each light fixture is determined online on an average of 25 watts. And operation hours per day, it would be 8 hours. And it is assumed. So the lighting levels that we have found is that when the lights are off, the natural daylight would be 602.8 lux, while the light intensity when the lights are on during the night time is 707.4 lux. So when we conducted a ventilation audit, it involves inspecting and assessing the performance of ventilation equipment and identifying areas where air circulation can be improved and ensuring compliance with the health and safety standards. So what we have conducted to accomplish this energy audit for the ventilation system is by recording the volume of air ventilation and the fan motor nameplate, and the local code requirement was determined and compared against the measurements, and the ventilation rates are checked to meet the code. So when we found was that the electrical fan motor horsepower was about 72 watts, and this is in accordance to Panasonic. The hours of operation is assumed to be 24 hours, and the electrical efficiency of these fans is 0.87. The airflow rate from the fan and outside room was calculated to be 8,417.46 cubic feet per minute. When we have calculated the air change rate per hour, which is the cubic feet meter per minute of the airflow rate to the volume of the room, we have found that the air change rate is about 119.17 per hour. So according to ASHRAE 62.1 standard, it recommends that the air change per hour should not be any lesser than 0.35, and we have found that this exceeds the code by a lot, which there is room for improvement in terms of ventilation rate. In terms of temperature audit, the process began with determining the indoor temperature and relative humidity setting of the rooms. The spaces that are unoccupied are also noted. So when temperature and humidity that exceeds the recommended temperature and humidity standards set by ASHRAE is recorded. So what we found that the average relative humidity or internal of the room is 54.48%, while the internal temperature is about 91.28 Fahrenheit. So the ASHRAE guidelines recommended that during summer, the recommended temperature should be in between 72 Fahrenheit and 80 degrees Fahrenheit, with a relative humidity of 30 to 60%. So we have found that the temperatures are not up to code, and we have to retrofit air conditioning in order to ensure the comfort and safety of the occupants.
Now, in terms of improvements, there are many enhancements that could be done to Village 1B, especially in doors and windows, such as installing weather strip doors and installing weather strip windows, and by making sure that the fans installed inside the rooms are high quality, and which will lead to a better air circulation. Now, the advantages of employing these changes will result in improving energy efficiency as well as indoor comfort, and low maintenance will be required, and which will lead to comfort the students, especially during the semester. Now, the outcomes of employing these changes is going to increase the energy efficiency as well as the cost saving will be significant from 2 to 3 years. And lastly, it will promote a high comfort.
So what we have found to improve the energy audit was to install LED lights and replace it from fluorescent lights and install sensors that detect occupancy. So this will ensure higher efficiency rate, which reduces the power and energy use, as well as reducing the hours of electricity used by these lights. We would also like to install variable speed drive. This is to reduce the wattage of the fans by instead of replacing the fans completely, while this adjusts the fan speed based on the required airflow and thus reducing energy consumption when full speed is not necessary. So the impact of this is lower fan speeds reduce power consumption significantly. And last but not least is to install air conditioning. While this requires some expenses, it is to reduce the temperature to ensure that the internal temperature is up to the ASHRAE code. So when we conducted the economic analysis for the lighting audit, we have calculated the annual electrical consumption is evaluated by calculating the total watts, power density, existing power density to the Code of Design guidelines, estimate the annual hours of use, and estimate annual lighting energy costs. And once we have found that, we will compare it to the retrofitted design by calculating the new total of energy use after retrofit and determining the annual operating hours if the light controls are replaced. So the energy cost savings is also calculated. So when we have So when we have calculated this, we have found that the electrical savings in a year would be about 1,293 ringgit and 73 cents. While this may not seem a lot, it is still considered a saving. When we conducted a ventilation and temperature audit economic analysis, we have found that the building size is approximately 3,456 meter cube, and the room size would be 120 meter cube. The airflow rate would be 8,417.46 cubic feet per meter. And when we reduce the air change rate to 706.3 cubic feet meter, which is at 10 hours per rate, we have found that the savings due to the reduced wattage is about 24,024 watts, and the savings in electricity costs would be about 91,548 ringgit a year, which is large. So when we retrofit air conditioning into rooms, we assume that the hours of operation for AC would be about 10 hours per day, and we will calculate the number of annual hours of wet bulb degrees over 66 degrees Fahrenheit per week, and that would be about 70 hours per week. This is all an assumption. Considering the relative humidity is about 54.48%, which is collected by data, the energy used per year for every 1000 cubic feet meter would be about 7 times 10 power 6 BTU for every 1000 cubic feet meter. So what we have found that the total expenses that is additional to this retrofitting air conditioning would be about 7,348 ringgit and 41 cents per year. So based on average prices in Malaysia, the cost per weather strip window is estimated at about 300 ringgit, and for insulated doors 400 ringgit each. With 28 windows and 28 doors to be upgraded, the total cost for the windows would be 8,400 ringgit and the doors would be 11,200 ringgit, which will lead to a total improvement of 19,600 ringgit. Considering the capital cost of the LED is only 65 ringgit per unit, and the total cost of the LED units for 77 light fixtures would be 4,875 ringgit. The installation cost is assumed to be 20 ringgit a fixture, so the total installation cost would be 1,540 ringgit, leading a total capital cost of 6,460 ringgit. A cost of the VSD is about 47 ringgit, and thus will be installed in 28 rooms and will account for 1,316 ringgit. The cost of air conditioning per unit is about 799 ringgit per unit, and thus the total cost to install air conditioning in all rooms is calculated to be about 22,372. The installation fees will be about 200 ringgit per unit, so the total installation fees will be about 5,600 ringgit, making the total cost, capital cost of the air conditioning unit to be about 27,972 ringgit. The payback period for this insulation improvement would be about 2.9 years, while the payback period for electrical device improvement would be about 0.405 years, making the feasibility of these retrofitting improvements to be extremely coveted for. Thus, to summarize, upgrading Village 1B's windows and doors to weather strip models will greatly enhance energy efficiency, lower maintenance costs, and increase indoor comfort. The suggested improvements include the installation of weather strip windows and doors, which will lead to significant energy savings as well as a quieter, more stable indoor climate. Implementing these changes will result in overall improved performance, comfort, and cost savings for Village 1B. The building is oriented towards the northeast direction. This orientation ensures that the structure is not directly exposed to the sun's beam in the morning and evening. Instead, it is positioned at an angle that allows for optimal natural lighting. The structure is predominantly lit by sunshine from the northeast during the day, gradually transitioning to the southwest in the evening. The peak cooling demand is observed at midday when the sun is positioned directly overhead the building, and V1B is the area that receives the highest amount of solar radiation. Roof structures are positioned in the front of the building to offer shading, hence diminishing energy losses. The building receives a constant amount of sun energy throughout the year because it is located near the equator. V1B benefits from this orientation by minimizing direct exposure to the powerful afternoon sun and lowering unwanted heat buildup, resulting in a more pleasant internal environment. So the energy audit also of the ground floor revealed significant opportunities for enhancing energy efficiency and comfort. The audit recommended retrofitting LED tubes in place of fluorescent lights, reducing fan wattage, and installing air conditioning systems. Switching to LED tubes significantly lower energy consumption due to the higher efficiency and longer lifespan, thereby reducing electricity costs. Implementing these measures to reduce fan wattage, such as installing variable speed divisors, will further decrease energy usage. So these systems designed for high efficiency will work in collectively with the improved lighting and fan systems to create an optimal indoor environment with minimized energy expenditure. Thank you very much.